Well, hello and welcome to Improving Health and Revolutionizing Insurance with Epigenetic Tests. So much has been happening in the field of epigenetics and the way they might be applied in insurance that we felt the need to come up with another video to provide an update and more details, and this is that video. We've got to introduce ourselves. Allow me to introduce myself. I'm Tom Nodine, the founder and CEO of Human Life Expectancy, Inc. My quick story is this. For most of my career, I've been an insurance executive, having led innovation and technology strategy at Allstate for a number of years, and a consultant. I led Booz & Company's insurance practice in the US and KPMG's global insurance strategy business for a number of years. And across all that time, spent much of the focus on implementing new technologies in insurance. And so spent decades working on digitizing sales, service, and claims, and putting new technologies of all types in place, including driverless cars, etc. But then in late 2016, I ran across epigenetics and the possibility that it represented for revolutionizing insurance was so much greater, really, than anything else I had seen, that I decided I really need to focus in on that, and ultimately ended up founding the company called Human Life Expectancy, Inc. And our major objective right now is to help as many people as possible to live as long as possible, as soon as possible. But the first way we plan to do that is actually to bring epigenetic testing to insurance. And so with that in mind, we also founded the Human Life Expectancy channel on YouTube to talk about kind of the broad history of human life expectancy, as well as epigenetics and other technologies that really offer the prospect of increasing human life expectancy. A whole range of things that could actually shorten human life expectancy going forward, and then a whole set of videos on, well, if we are going to be living longer, what does that mean for our lives, for our businesses, for our economies, and for our societies? So we've put all that together. That's me. As I went on this journey, there is nobody that I would rather go on it with than Raymond McCauley. So Raymond, would you please introduce yourself, and we'll get going.
Sure, let me give that a shot. That was a great introduction, Tom. I'm Raymond McCauley. I am a computer scientist, biophysicist, and molecular biologist. I have been working and doing some super fun and interesting things across the engineering, science, and business in the field of biotechnology. I'm kind of known for being one of the founders of Singularity University, which was a fantastic place where we look at exponential technologies and how they impact the world. Being one of the founders of BioCurious, the world's first hackerspace for biotechnology. And I do a lot of work now where I am advising companies, governments, investors on how biotechnology impacts their future plans. But several years ago, I was working at one of the biotechnology companies as a principal scientist at Illumina, and we did a lot of work on developing the first really high-speed, large-scale human genome sequencing. While I was there, I had worked on all the informatics for the very first base-level human epigenome, and was working with fantastic scientists in San Diego at the Salk Institute on how are we going to use that information to really sort of pull back the covers on the mechanisms of human disease and aging. And it wasn't too long after that that Tom and I first got our chance to meet in Chicago and kind of started on this journey together.
Raymond, thank you so much. And again, I'm delighted to be on this journey with you. So why don't we get started? I should say at the outset, though, we already have a video out on epigenetic testing and genetic testing that goes into some pretty great detail about the history and how they were developed. And the main focus of this is going to be to build upon that video to talk about where it is today, recent updates, and specifically its application in the insurance sector. But just because you could certainly be forgiven for not being up to date on all the details of genetics versus epigenetics, well, why don't we start there, Raymond? How would you describe the difference between genetics and epigenetics?
Sure. Here's my little, 5-minute graduate degree in a box, right? Whenever you look at genetics, which people are more and more familiar with because we have different kinds of genetic testing, different sorts of ways to look at what our code of life is. This is all coming out of the Human Genome Project, which we've been working on for, kind of stopped working on it in 2001, 2003, but have been reaping the fruits of that labor. And the genetic code is an alphabet, a series of A's, C's, G's, and T's that go ahead and specify all of the proteins and how they're made in the human body. And then the part that we have understood a little bit less, but are getting a better and better grasp of, it's also the part that tells you when to express those proteins. So whenever we talk about that genetic code, we're really talking about a parts list. And think about that. You're building IKEA furniture. You've got that parts list of all the different pieces that you're supposed to have in the box. And if you're missing one of those pieces, you're kind of in bad shape. Now, epigenetics is a code that rides on top of the genetic code. And so it turns out, just a quick little dive into it, the A's, C's, G's, and T's, the C's can have two different forms. One is just a cytosine, a C in that double helix of DNA, but sometimes you can have on top of that cytosine a methyl group, and we call that a methylated cytosine. There's all sorts of things. You'll hear people refer to these as CPGs, etc. Don't worry about that. Just know that basically the best, simplest diagram shows like a lollipop sticking off the side of the DNA. And it really is that. It's like a bump. It's almost like a speed bump. And what it does is it keeps proteins from latching on and doing things, reading the DNA as you go along. So this epigenetic code is sort of a way to alter part of the genetic code to make it easier or harder to read as you go through. The way to look at it whenever we talk about the parts list and the genetic code, the epigenetic code is sort of the assembly instructions. It's like, this is when you need these parts. This is when you should be using this and doing this. And then with your permission, without going too far into the science, it's been really interesting. We've known that epigenetics is something that exists in all mammals. We know that that code is something that is super important from the moment that life starts, because one of the big things it does is it tells every cell what kind of a cell it is. It's the difference between a bone cell and a brain cell, which of the proteins are turned on and which ones are turned off. But even more than that, that change of what it is, it also kind of tells the cell when it is. So as a cell goes through its different things, a bone cell and a brain cell both are very different, but behave very differently at the start of life, and then as you go through the different stages of life, all the way to the end of life. And as we'll talk about more, Steve Horvath, kind of the guy who got there first with a big team, but he gets to name it, came up with this way of looking at epigenetic testing to tell where you are in sort of the cadence of life. Almost, how long do you have until you die? We talk a lot about that piece. So epigenetic tests can be used for all sorts of things, but especially to tell a kind of biological clock.
Mm-hmm. Can you also elaborate on the changing of genetic code versus the changing of epigenetic code over time? Right? They're not, as I understand it, they're not the same.
Absolutely. And the simple way, although there are exceptions, the simple way is that genetic code is pretty much written in stone. It is what you get from mom and dad at conception, the beginning of life, and with a few bad exceptions, it doesn't change. And it's the parts list, it's there in every cell. The epigenetic code changes a lot, where that methylation that happens determines which genes are turned on and off. And it's the natural way that these cells, like I say, know what their identity is, and even more so know what they're supposed to do when. And so looking at those changes over time, we can see what kind of cells we're dealing with, if they're in a healthy or unhealthy state, if they are sort of moving along this natural progression from youth to sort of maintenance to more, we'll call it duct tape maintenance, where things are starting to go wrong and you're kind of trying to patch it up. And so it's something, there's a lot of different ways that we study gene expression, the ways to see which genes are turned on and off. This has turned out to be a really great way where it just works so well in universally in every animal, every mammal, every cell type, and at every point in time, and very consistently is telling you this is what stage a cell is in. This is whether or not it's responding to disease, environmental conditions. So it's amazing. It's this ever-changing, super complicated code that we're really just learning to decode, and have learned a huge amount about in a very short time.
Great. So Raymond, would you humor me by listening to kind of the way I think about this, and please let me know whether I've got it right or wrong?
Absolutely. And I love your take on this.
Okay, so the way it occurs to me is that our bodies are even more fantastic than we thought they were. Not only do our genes evolve generation by generation through homologous combination with our mates, as we all know, and that's fantastic, and this is Darwinian evolution and all of that sort of stuff. That's very cool. But even more cool than that is epigenetics. The genetics, as you said, stay the same throughout your lifestyle except for very minor mutations in all your cells. So what's good about that is you can read a consistent code. But what's bad about that is that makes genetics completely useless for diagnosing changes in your health, because the genetics doesn't change, it's just there. But the part that's more fascinating now about our bodies is that when we do things, so let me just choose an example. I don't smoke, but let me say I smoked. If I were to smoke, what actually happens in my body is my body goes, oh my gosh, what did you just do to me, right? And it goes up and down all of the CPGs, the surface of the genome, and it turns on some genes and it turns off some genes, and it does through these methylation patterns you describe. And it leaves a record of what your behavior has been, but even more important than that, it adjusts your genome within your lifetime to turn on the genes and off the genes so that you can better adapt to whatever behaviors it is you're doing, whether it's smoking, whether it's consuming alcohol, whether it's dieting, whether it's exercise, whether it's sleep. And so epigenetics becomes a record, now that we can read it, of kind of what your behaviors have been, and even kind of what diseases you might face and how your body is responding to those diseases. So let me stop there. Have I gone too far, or does that seem roughly right?
No, that's great. And you covered a point that I left off of the story, which is that it's not just the control system that's going through, it's also kind of a ledger, right? That is keeping up with, or that has got a history of all the genes that have turned on and off, what's going on there. And it's a fantastic way to look at it.
Yeah, great. And to me, that's what makes this stuff, we're going to get into this in much more detail, but that's what makes this so interesting for insurers, because insurers can then participate in monitoring the behaviors that determine the health of most people these days. 3/4 of us die from non-communicable diseases. Things like heart disease and cancer and stroke and diabetes and all that sort of stuff, all of which can be impacted by our behaviors, what we eat, how much we exercise, how much we sleep, stress, and all these other things. So it kind of opens up a world to us that has never been opened before. So super, super exciting, and we'll talk about that more in a few minutes. Would you please describe a little more about how the tests actually work? What do you do to take a test?
Sure. And a lot of this testing is new, and the way that this is working is evolving, but the idea is you want to get some cells from your body, You want to get some tissue type. And it's not that different from how a genetic test works, because again, you're looking at either one of them, you're looking at DNA. And so you want to get some cells with DNA, which is pretty much all of them. And the two easiest ones that we always like to target are saliva, that have got cells from your buccal cells, your cheeks.
Your mouth, yeah, your lips and things, yep.
Or blood cells. And so like a simple little finger prick, not even a blood draw, either one of those works to get blood. Saliva, you just go ahead and spit in a tube, or you go ahead and directly collect cheek cells by rubbing a swab on. And honestly, that's kind of where it begins and ends for somebody collecting cells, but that's where the journey starts in the laboratory. You send those off. That DNA is very stable at room temperature in the mail, and somebody can get it in a lab in a matter of days. And then we go ahead and go through steps, dissolve the cells, bring the DNA out, take it, and we can look at it and we can sequence the DNA. And it turns out that looking at the A, C's, G's, and T's for a normal genetic DNA sequence, that vanilla, not changing part, that's still good, important genetic testing that can show you whether you've got predilections for different diseases, those non-communicable diseases you were mentioning. But then going ahead and looking at the epigenetics, it turns out we can go ahead and do that by looking at which kind of C's you've got in those same places. And there's a bunch of ways to do that. You'll hear people talk about bisulfite sequencing. You'll hear people talk about nanopore sequencing to be able to directly tell that kind of base. There are ways to do this with microarrays, with differential PCR, all different techniques. And these are things that we study. And by we, I mean you and I really keep on top of what the different methods and techniques are and how they're evolving, because we're really concerned about these tests and the prices of the tests, right? We're looking for the best and cheapest way.
Yeah. So these tests can tell us all kinds of things. They can tell us our biological age. They can talk about, or they can reveal historical behaviors, such as drinking behaviors, smoking behaviors, and that's important when we get into talking about fraud in insurance, as well as just mortality risk. And of course, there's diseases too. So I guess that raises the question. You said many people are doing these things, so if every man and his dog is coming up with an epigenetic test, how good are these things anyway?
Well, the test itself, to go ahead and sort of count up which ones of these cytosines are methylated or not, and where they are, is, I won't say it's a done deal. It's something that's constantly being refined. But how do you then interpret that? And we haven't really talked about this idea of a biological clock very much. Maybe this is a good time. So Steve Horvath, being the pioneer in this, had come up with this way where basically they realized, whenever you look at all these cells over time, that the methylation does change, and it changes as you're going, and it correlates really, really well with age. And whenever we say age in common conversation, we mean calendar age. We mean, when is your birthday? How old are you? Right? But it turns out, and we all know people like this, there are some people who are aging a little bit faster and some people who are aging a little bit slower. Right? And, that whole, oh, you look so good for your age. I wouldn't believe that you're 40. And of course, I know enough to go ahead and always take off 10 years whenever I'm guessing somebody's age. You don't want to do that wrong. But it turns out you can do a really good job. It correlates really closely to the calendar age. But Horvath and some of these other folks said, what's interesting is the times when it doesn't correlate well to the calendar age. We have some of these people who really do, they're 40 and they look like they're 30 biologically, internally. We have some of these people who are 40 and look like they're 50. They've kind of, had that hard life and what's going on. And so it turns out that folks that are at the extremes here were showing off basically things where, because of environmental things going on, lifestyle. You mentioned smoking, exercise, drinking, things like that. Two of those bad, one of those good. Looking at the different things that they have done for their own medical maintenance and upkeep. Looking at things that are kind of, accidental, right, that have happened, environmental insults that they have basically then aged and are further along that biological aging path, or are earlier because they're doing such a good job of things. And so that has become very interesting. And Steve, when he talks about this, switches it around and talks about basically being able to determine all-cause mortality, that this is a clock or a fuse that is sort of ticking down, and we can tell when someone is getting closer and closer to death, or, and this is the even more fascinating part, so if you had a biological clock that could actually tell you when you were going to die, that sounds like something out of the Twilight Zone, but what you really have is something that tells you how hard your body is working against problems. And now that we are being able to, and this is one of the breakthroughs that we've made in our little group, separate out what these different problems are. It looks a little different when somebody is dealing with cancer and high cancer risk. It looks a little different when somebody is dealing with cardiovascular risk. It looks a little different when somebody is dealing with different obesity related and blood sugar problems and things going on. It even looks a little different when somebody is dealing with different communicable diseases. And so all of these leave a different pattern of marks. And so not just being able to say, this is the time span that somebody has, but being able to say, these are the things that they're really at risk for. And more to the point, if you can do that, and it's not, again, written in stone like your DNA, your epigenome, can you do things to really change this? And let me stop there, because I think that opens up a whole real wave of possibilities for individuals, for science, and for insurance.
Absolutely, it does. So, as I read Steve Horvath's work when it first came out and started thinking that, of course, the insurance innovation guy in me came to this staggeringly obvious conclusion that, holy smokes, this has a lot of impacts for insurance. If you can, number one, predict more reliably how long people are going to live, that's of enormous value to life insurers and to health insurers. But as you say, even more important and more valuable from an economic standpoint is the possibility of helping people to live longer, right? And so these benefits just kind of came out. And so the number of things that you can discover through epigenetics is growing almost weekly. There's a new article that says there's some new disease that you can find with epigenetics. And so the list of uses for it are going. But I think it's important to say, and I'd kind of appreciate your view on this too, epigenetics as a science is really in its nascency. While we've found these, what I call threshold applications, an application that is clearly useful, that makes the test worth more than its cost right now. So it's kind of above the threshold, or as insurance people say, it has positive protective value now. But the real thing is, it's going to be worth more and more and more over time, because the same test will be able to uncover many, many more behaviors, as well as medical conditions and other things as well, and identify, as you say, specific interventions that are right for each individual. Did I get that right?
Yeah. I love the way you look at that way. And I would say it's kind of a mixed bag, but in a good way. It is a super new science. So it was something that was really discovered, this idea of a biological clock, less than 10 years ago. 2015 is when we saw some of the first real pieces.
Yeah, Horvath is November 2016, right?
There you go.
Yeah.
And people were only starting to talk about it and say, is this right? Like in 2013, 2014, 2015. So seeing the first published work on this less than 10 years ago. But we are already to a point where we've sort of gotten over the skepticism of a biological clock, really? And does this really work? Well, maybe it works for this, but not for that. Pretty much it works for everything all the time in every tissue, animal, situation we've looked at, except for maybe being hit by a bus. And even then...
That's right. And by the way, it's important to mention that. I mean, approximately 9% of the people around the world die from injuries. And epigenetics, unless there's something related to your ability to avoid injury, by like you're smart enough not to do stupid things or have quick reflexes or something like that, probably is not going to impact the injuries much.
Well, and we were having that discussion over the holidays. It's like, well, this doesn't really apply for being hit to a bus. It's like, well, no, but if you're slow moving and don't have good eyesight, it turns out that you are hit by buses more often. So really, it's kind of across the board. There are thousands and thousands of years of curated health data that have now gone into these predictive regression algorithms, or it's now much more in vogue to say machine learning AI algorithms, and it's all the same thing. And we're able to predict really well. The exciting thing is we are moving from being able to do statistically significant predictions of biological age for groups of people and for stratified groups of people more and more to smaller and smaller stratified groups of people and individuals, and even being able to see the effects of individual interventions, doing more exercise, improving diet, taking certain maintenance drugs, or skipping the maintenance drugs. We can differentiate between somebody who has smoked a pack a day of cigarettes 5 years ago to someone who has done it 10 years ago, to any variation, much better than somebody can self-report, even if they're being completely honest, on a simple questionnaire. And so this whole thing has turned into a really high-resolution way to look from groups of people to smaller groups to individuals, from all-cause mortality to any branch of mortality that you can think of. And like you say, as an insurance person, this is very predictive, but as an individual and as a scientist, this is helping us figure out causes of disease and interventions. As a person who just wants to live longer, this is something that you can really start to use almost as a personal clock, and to rate and rank different things that you're doing to do a better job. And in some ways, this is, I think, what has us both so excited. It's a revolution in insurance where instead of making a bet on this is how long someone's going to live actuarially, you're really saying, hey, we would love for you to live so much longer and keep paying us premiums, and so we want to give you these tools and this new information.
It turns out that's where the money is anyway.
Yeah.
And so this kind of narrow view that the only way you're going to make money with genetic testing or epigenetic testing in insurance is by using it on the underwriting side is wrong. There are underwriting applications, and we'll talk about those. But the biggest gains, we think, and also our insurance partners we're working with now, are absolutely focused on the notion of helping their customers to be healthier. So we'll talk about that. But back to the core question of how good are these things, I remember doing an analysis which basically showed that epigenetic tests add as much explanatory power to your expected lifespan as knowing whether you smoke or not. It's kind of plus or minus 7 years. I mean, it's a big deal. This isn't like a small rounding error thing. And also, it's factors that largely have not been captured by common underwriting processes or other medical tests. So these are really kind of new, exciting information with great applications.
And I would even say that's the old piece that, that plus or minus 7 years comes from a study that has existed for a while. That's the worst it's ever going to be. I think that we're getting up on better and better numbers and better discrimination.
Better and better all the time. And the thing that we need to make it better is more data, right? And so that's where kind of the philanthropist in me kind of gets up and says, well, hold it. There's a duty here, or not a duty, or at least an opportunity for insurance companies to absolutely benefit humanity. What insurance companies have is large numbers of people that are interested in improving their health. And by the way, they have a big financial incentive in helping them to be healthier. Well, by collecting this data, we can get lots more information that will then further refine the predictors, expand the predictors, and help us all. So it's not just that this is all good from a narrow money-making perspective within insurance, although I think I can make a pretty good case that it is. I think it's much bigger than that. And that's, by the way, why we named our company Human Life Expectancy, Inc. It's the bigger picture. We really want to help people live longer, and I think it's quite credible that this is an approach that can make that happen with the partnership of insurance companies.
Absolutely. And from a scientific side on that, whenever we look at these scientific studies, the best ones, run for 10, 20 years and go ahead and collect data as they go. It's incredibly expensive, and you're very limited in the number of people that you can look at. Or contrary-wise, what you do is you say, we have somebody who's done that study and banked a bunch of samples that we can go back and retest from 20 years ago and look at what it was then and look at what it was at the end of the study and maybe through. But again, very limited. So the idea of being able to piggyback on the work that insurance companies already do for millions of people, where they are at a high resolution tracking outcomes, is super exciting, and for so many reasons to have that huge statistical power. But just to mention one, whenever we talk about things like cancer, half of us are going to die of cancer. But whenever you look at particular cancers, each particular one for any given person in any given year is very rare. It's like a 1 in 10,000 thing in the population. So having those large numbers really lets us race ahead to both predicting what's going on and to figuring out how this works, and then being able to help people throw up guards against these things much faster than what I would call kind of conventional scientific research, right?
So there really is a humanitarian need or opportunity here to help humanity and help us all live longer.
I think
that's great.
A great way to race to the goal. Yeah.
Absolutely. And so if I think broadly about, now if I put my consultant hat on and I say, okay, well, how is this of benefit to insurance companies? I think there's really 5 things. The one we've been talking about right now, and I think it is the right first one to talk about because it's the best one from a humanitarian standpoint as well as from a financial standpoint, is helping customers to live longer. The simple thought is, what can be measured can be optimized. And since the beginning of time, we've all been trying to live longer, but it's kind of the equivalent of dieting without a scale, right? We've never had a scale to say, well, all right, you go running and you eat kale and you meditate and all that stuff, but net, how much longer does that mean you're going to live? Well, before biological testing, but biological age with epigenetic testing, we haven't had a reliable way to answer that question. But now we do. And so what needs to happen is, let's test a whole bunch of different interventions for different people and discover which ones have the largest impacts on biological age, in slowing or even reversing biological age. And there have been numerous studies out that show that this can happen with an intervention as short as 8 weeks. Many studies are getting 3 or more years increase in life expectancy. So that we're really kind of at early days, and I think this health benefit is an enormous one for humanity and others. But it isn't the only one. There's actually 4 others. One, and if you'll excuse me here, because I know this insurance stuff isn't necessarily your bailiwick, at least right now. But insurance companies have an issue, especially life and to some extent health insurance companies, in that they charge premiums over time, and then the payment in the case of life insurance is only after you're dead. And in the case of health insurance, there's kind of an asymmetry. Of course, the customer wants the claim payment, but not every claim can be paid, and there's fraudulent claims, et cetera. So the insurance company is on the side of kind of minimizing claims. And so that creates a really bad relationship. You're charging premiums all the time, and the customer gets paid back either after they die or in a way that is perceived as minimal. Neither of those is good. Well, imagine how you can turn the public relations of your insurance company around by saying, you want to live longer, we want to help you live longer, and we can do that, right? And we've got tools now. So by using epigenetic tests and using them in a longitudinal way or a time series way, we can actually track, well, here's how you're doing in terms of managing your life expectancy over time. And so revolutionizing the customer relationship from an adversarial one to one where you're working together to live longer is of enormous brand benefit, marketing benefit that'll impact the bottom line. The third benefit is of course pricing. Yes, if you can predict more reliably how long somebody's going to live, you could price an insurance policy accordingly. So on the positive side, if you get somebody who's going to be living longer, you can afford to give that person lower premiums because they're going to be paying those premiums for longer, and the time that before which you're going to have to pay the claim is longer. And so there's actually quite a lot of money on the line in life insurance to helping people live longer. And you can compete effectively by offering people who have longer life expectancies lower premiums.
And Tom, if I don't mess up your flow, may I interrupt you here for just a second? Because this is something, and I do love this because I think it's so great because this enables us to help people do some great things and do some great science while also fitting into existing business models, right? And one of the things we have had people talk to us about is that pricing and that piece where it's like, well, but if you do genetic testing, you're finding things wrong with people, and so you're going to basically penalize them by offering them higher premiums. But we've talked about how this really enables this possibility of upside pricing. And is this a good time to mention that?
Yeah, I think it is. So I think people are properly concerned about sharing their genetic data because it doesn't change ever, and because it is the code of life, expression or not, which is the epigenetics piece. It's probably important to know things like, well, do you carry the genes for Huntington's or other big diseases? And you might not want to share that information with everybody. That absolutely makes sense. And because of that, in the United States, there's something called the Genetic Information Non-Discrimination Act, or GINA, or GINA. I don't know, well, I think I do know about you, but I'll speak just for myself now. I mean, I want to live in a world and in a country where people are not penalized for the genes that they happen to have born with that are not at all their fault, right? To me, that just seems like a fair shake way to live, right? And so GINA says effectively that for health insurance in the United States, it is against regulations to use genetic, not epigenetic. This is really important. But it is against the regulations to use genetic information to determine the pricing of health insurance. The thinking being that health insurance is an absolute necessity. You can't live without it in today's society. Interestingly, though, that is not the case with life insurance. And again, I'm not a lawyer, so please, do your own legal analysis on this, but here's the way I understand it, that the Genetic Information Non-Discrimination Act does not apply to life insurance because life insurance is considered discretionary. What that opens up the possibility of doing is using genetic data even for life insurance. But I think life insurers are appropriately reticent to do that. Who wants to be the first life insurance company to say, hey, we're going to take the genes that you happen to have been born with and use them against you? No one wants to do that. And by the way, we're not fans of that either. But several things here. Oh, go ahead.
Oh, I was going to say, and we've talked about this. I've testified in front of different government bodies on sort of that same thing. It's like, yeah, genetic testing looks at inborn tendencies to develop or not develop a disease. And we seem to have made sort of a societal decision, hey, we don't want to penalize people financially for the way they're born, for, what they're starting off with. But this idea that lifestyle, things that you choose to do, that you have the freedom to change, and everything from, smoking, drinking, how you may progress with weight gain and different things like that. Mm-hmm. And so that's really, in so many ways, the difference between that genetic and epigenetic. But I interrupted you.
So you put your finger right on it. The core distinction between genetics and epigenetics is that genetics are the same in every cell of your body throughout your entire life, never change. Epigenetics changes dramatically. They've been proven to change dramatically based on your behaviors, based on your age, based on diseases you might have. So in that sense, because it changes, it's actually no different than, for example, a cotinine test that's used for your to determine whether you smoke or not. So insurance companies typically analyze your blood and they look for cotinine, which is a metabolite of nicotine, thus the name cotinine. And the thing is, cotinine only stays in your blood for about 16 hours or so, right? So if you don't smoke for a day or two, your blood looks like a non-smoker's blood. And because of this, a lot of people are actually fraudulently applying for insurance and getting non-smokers rates for when they are actually smokers. Well, not so with epigenetics. Epigenetics, again, it's your choice to smoke or not, but it will impact your epigenome in a long-term way so that you can actually tell, approximately how many cigarettes somebody has had throughout their life, not just, did they have one within the last 16 hours. So that actually leads to another potential benefit for insurers, which is they can really help cut down on fraud. And there's a lot of fraud, as I just mentioned, in the application process for smokers trying to pass as non-smokers. And by the way, it's even worse for those who abuse alcohol. Alcoholics have mortality rates that are 4 times the rate of non-alcoholics, and so the premium should be much higher. But, excuse me, but if you don't take a drink, several hours before, no one's going to know. And often all that's done from an insurance standpoint is a fill-in question on your application about how many drinks you have a month, approximately. And there's seldom ever any follow-up on that. Well, with epigenetics, you can be much more precise about that. Mm-hmm. So I want to make a distinction here between the science and the business. From a science standpoint, it is just factually true that you can now tell a lot more about somebody's historical behavior than you have in the past. And that includes smoking and drinking and other drugs and that sort of thing, right? From a business standpoint, there are very good reasons why you might say, all right, even if I know that, I don't necessarily want to penalize somebody for that. And in fact, the vast majority of insurers we work with do not want to do that. And they basically say, look, what we're going to do is if we use this at all in the underwriting side, it'll be in what we call an upside-only way. What they say is effectively, look, we'll underwrite your insurance the way we would always have underwritten your insurance as a baseline, right? But if you're willing to give us a saliva sample, we might be able to reduce your premiums by up to 50%. That way, they're no worse off than they were today by offering the same terms that they would have to the same people. But they also give those people that are going to be living longer lower prices, which helps their competitiveness. And by the way, it helps their book of business because they end up having a more healthy book of business and their customers end up with adverse selection. Mm-hmm. But again, this is the pricing or the underwriting benefit of epigenetics, and it is generally not the main one that insurers are interested in getting for all the reasons we've talked about, right? And I guess the core thought again is, I think many of us want to live in a society where the things that are beyond our control are absolutely not used against us for insurance or any other reason.
Really aligning those incentives where it's like, if I am sharing this information with you, I'm not getting penalized for bad stuff. I'm getting rewarded for good stuff. So yeah, let me share more information. Let's do more good stuff. And there's that virtuous cycle. The more good information we have, the better these tests get at helping us find things that help people.
Exactly. So I had mentioned that there's 5 benefits for insurance companies. Believe it or not, we've hit 4 of them now, which is good. We only have 1 left. The one that's left is actually process. Today it costs about $400 on average to medically underwrite somebody for life insurance. It's notable that that is already much more than the cost of an epigenetic test. And epigenetic tests can actually tell you in many ways more than normal underwriting would. And even then, there's one of the major areas of growth in insurance these days is life insurance in India, China, many other countries where the middle class is rising quickly. But what is not in place in many of these countries is a nationwide chain of phlebotomists that are available to go and draw blood and do this analysis. So in that space, what insurance companies are doing in those areas to take advantage of the rise of the middle class and helping them get the insurance that they want and need is say, look, we'll do accelerated underwriting, based on the best mechanics and understandings we have right now. But again, if you're willing to give us a saliva sample, we might be in a position to reduce your premiums that much more. Reduce the premiums, increases the penetration, increases the growth, and again, gives you a more healthy book of business. So those are kind of the 5 things. Again, it's health, helping customers to live longer. It's changing the relationships with your insureds. It's the pricing and underwriting benefit. It's the fraud benefit, knowing more about whether somebody smokes or drinks or not, and a range of other behaviors. And then finally, just on the process side. So those are the 5. So, as we've been talking about this, I like to think about, what does an ideal insurance partner look like? And I have some thoughts on this, and I'm interested in your reaction. You game?
Yeah. Please hit me with it.
Okay. So, first of all, first and foremost, we're looking for partners that want to help their customers to live longer, because that, I think, is the core promise of the epigenetic testing. And of course, the core promise behind our business of human life expectancy. So, those insurers that are low cost only, not looking to innovate, not looking to deepen the relationships with their customers that way, are less likely to be interested in us, and candidly, we're less likely to be interested in them. So that's kind of the first thing. Second thing I think is important is a company that recognizes and is driven by science, not just spin and marketing. You know this, Raymond, but I'll say it here. The reason we have you, and we have Miten, who's our chief science officer, who's also a world-renowned epigeneticist, is that science is the beating heart behind what we do. We never want to get ahead of where the science is going. And by the way, there's plenty of others that don't take that view and are willing to cash in on I'll say somewhat specious claims and less scientifically robust applications of the very things that we're talking about. So again, in addition to helping customers live longer, we want a company that recognizes and is willing to follow and be limited by the science of today. That's kind of another one. And I guess even more importantly, we're kind of looking for a partner or a range of partners versus a vendor. We don't view ourselves as selling a packaged solution, or here's our test, and you market our test, and we just show up and do it and keep all the data and everything. I think the way this is going to work best, and with our partners, the ones we're most interested in are those that are saying, yes, we want to work with you to customize the epigenetics to our specific country, to our specific population. And we want to learn for our people which are the interventions which will help them to live longer. That is something that we as a company can't land on the doorstep of your insurance company and say, we know the answers to that, and just listen to us and pay us this money and we'll do it. That's not us. That's not what we need to do is work together to make that happen. So, we absolutely have world-class predictors, and you described that a little bit. We'll talk more about that in a little bit. But we need to refine those and make them fully applicable for each insurance company's kind of population and groups of people. Does all that make sense?
Absolutely. That's super helpful.
Well, let me turn this back over to you. So I mentioned that I've been talking too darn much. So given that there are a whole range of epigenetic tests out there right now, including many that are available from a direct-to-consumer standpoint, right? And so I guess my question to you is, how do you tell a good epigenetic test from a not-so-good epigenetic test?
I've got thoughts on that, and I'm a little bit of a test junkie because I like to keep up with what's going on. I've worked on a lot of startups with different kinds of personal genetic testing and other things, or things around longevity, et cetera. I guess I've got a couple of rules of thumb. One of these, we've had a lot of different tests that will actually purport to tell you what's going on with, your general health or your biological age, and some of these are not even based on epigenetics. Everybody always wants to talk about telomeres, the telomere test, this idea that you've got something at the end of your DNA and it gets used up every time DNA replicates, and at some point your DNA would unravel. And so if your telomeres are short, you're close to that unraveling stage. And it's a valid concept scientifically. It's super interesting to look at how that relates to some diseases of aging. It is not very predictive individually. It turns out the error bars of that test and how we understand how that works are a little bit bigger than how well we can measure it. So the whole idea of measuring your telomeres individually has maybe fallen into a little disrepute scientifically. Anybody who is talking about this and is trying to sell you vitamins or supplements,
snake oil.
Might be a little snake oil, might be super well intentioned, but this is something where they're trying to sell you something. Anybody who is doing it and mentioning the word toxins, that is one of my red light words. Toxins means you're kind of trying to prey on fear or something. There's not a lot of biological science or medical intervention where they're like, you should worry about toxins. That's a red flag. Anybody who is doing this and is providing a lot of scientific references saying, according to this paper, or this is what we found this in, that is a green flag. That means that they are doing their best to make it current, true, and sharing the information. So I'll leave it at that.
And another aspect in determining whether a test is good or not is good for what purpose? If what you're trying to do is just truly just give a first indication and basically using the answer for entertainment purposes, fine. An out-of-the-box solution can work quite well for that. But there's a lot of things that those out-of-the-box solutions today won't do. As we mentioned, they won't be customized for a specific audience, certainly not an insurance audience, and perhaps not in your country. 2, they may not be adjusted for longitudinal use. Now, Raymond, you can back me up here. What we really should have is our data people talk about this in much more detail. But what they tell me is that it's really important to adjust the individual estimates of biological age for longitudinal use. And there's specific mathematical approaches for doing that we spend considerable time focusing on and absolutely do, because our objective, among many other things, is not just a one-time assessment, but assessing biological age over time. And that means figuring out, well, how has it changed over time? And if you don't do this adjustment for that, the data you have really isn't useful for that purpose.
Yeah.
What do you think about that, Raymond? Does that sound right?
Absolutely right. And it's a good point. It's a technical point, and it's something that is a little subtle. Not everybody's going to pick up on. A lot of these models have been set up to just basically say, here at one point in time is a rigorous estimate of biological age, period. But the way we're envisioning using them, the way we think that this is much more useful, is being able to reassess biological age at different times. And without getting into the statistical intricacies of, are you using a Cox regression or this or that, there's all these ways to look at it. One of the things that pops out is, if you're not careful, like some of these other things, you do an estimate here, you do an estimate there, an estimate there. The error bars on each one of those estimates are months wide at least. And so it looks like you're getting sort of randomly younger and older with no reason to it.
What about what I mentioned before, that epigenetics has actually been proven to be a cause of aging? In effect, one of the things that happens as we age is our cells forget who they are. And they start doing things that they weren't designed to do, or stop doing things that they were designed to do, and we age. So it is a fair statement to say, I think, and please stop me if you disagree or let me know. The research now indicates, yes, epigenetic deterioration is a major cause of aging. And that's different from other predictors of biological age. So for example, there's predictors of biological age right now where they look at kind of the number of wrinkles on your face and they can predict your age from that. Or they look at how quickly you get up and get down and all that sort of stuff. And while those may be indications of vitality, there's no doubt about that, no one is going to say that the wrinkles on your face cause you to age. Right? It's not a causal factor. So, I mean, if you're going to predict something, if something is going to be a predictor of biological age, you would think you would prefer to use something that has been proven to be an actual cause of aging. Is that right?
No, and that's good. And that actually brings up a couple other points if you'll indulge me. But the main one, and honestly, this was the people in the field who have been studying this, we did not know that was necessarily the case, and more evidence has come to light that that's absolutely the case. We're not just counting the rings on a tree. We're not just looking at the odometer. We have something where this is causative, right? And so we say whenever this happens, sometimes very directly, the mechanisms that are supposed to maintain the methylation in the cell, whenever they break down, the cell kind of goes rogue. It becomes a senescent cell, and that's a major cause of some different modes of aging. And so that's a big deal. But even beyond that, we're seeing that this is not just a readout. This is the way that cells control what they do and when they do it. And so it has all sorts of interesting implications. And let me mention, and this is, one's a little far out and one's really far out. One that's a little far out.
Okay, cool.
So you and I really believe in the scientific and business case for this being super useful and that they feed each other. But kind of the thing that it goes off even further, the place that this becomes not just useful for insurance companies, but, and I always want investors to know this, this becomes so universally useful as a way to keep up with how well do drugs work, how do different interventions work. Just on down the line, the ability to go ahead and say, somebody has been taking these pills for a year. Did that really improve their, not just quality of life in ways we can measure in other ways, but did that slow down their aging? Did it reverse their aging? And this is absolutely possible. We have seen this shown in some recent studies. That becomes amazingly valuable to say we've got a new metric that works universally across anything that is looking at how disease and aging interact and what aging is at base. And one way that that's even more useful that people don't think about a lot, like it's great whenever we have somebody and we can follow them for 20 years and we can listen to their heartbeat and we can see how fast they get up and get down and they can do the memory test. You can't do that with a bunch of cells in culture in a petri dish. You can't say, well, could you read that eye chart? But what you can do is you can do an epigenetic test. That becomes super useful because you can try out new therapies. You can do all sorts of studies. So this information that we are in the process of improving, and it just gets better the more data that goes in, this becomes incredibly valuable to humanity, to science, and to each of us as individuals, because we can use this in all sorts of things, and we don't have to wait 20 years to use it. And I'm just, and people don't necessarily get that, and we're really just seeing the big scientists in this field start to say, oh, but also in tissue culture, this is a big deal. And I think that that's a great point to make, and it becomes super valuable. And here's the other piece, and this is, and you've heard me say this.
And there's more. Yeah,
oh my going. God. The odometer story, and I hope you don't mind me telling this.
No, again. Go. I know it, but go ahead. Yeah.
So just this idea that people were so skeptical. It's like, so you're saying this stuff works like an odometer on a car, and I can tell the mileage on a car. And it's, yes, absolutely, that's true. We were kind of like, well, we think maybe, and now we can say with certainty for any kind of mortality, disease, for all these things, it varies exactly like an odometer on a car. Where this is magical, though, is we have started to see that we can do things where it's like, if you're normally changing your oil on a car versus not, you still are putting on the same miles. Well, this is actually working where it shows if you're changing your oil a lot, your odometer kind of slows down. You're driving 20 miles and it's registering as 15. What's really cool is now we have found some things where it looks like you can go in and just directly affect the epigenetics and crank back the odometer, which of course is illegal with my old Chevy, but I do that and then all of a sudden all the dents pop out and the engine starts purring smoothly. So not only is this a causative thing, it is something where we are finding ways we can intervene. Now, that's not a big insurance thing. That's not a big thing that I can do personally right now. But this idea that further on, all the science that we're doing and the information we're gathering helps us build a picture that we can now say more and more for individuals, here are these specific epigenetic surgeries that we can do that will help them live longer. It becomes sort of, I don't want to say a magic fountain of youth, but it's something that kind of starts to creep up and look a little bit like that. It becomes a basis for a therapy that we can't do now, but we think we'll be able to do in the future.
I love that you brought those things up. And in general, that's what I love about this whole field. We are absolutely in our infancy here. And really what I view our job right now as being is, let's find that first large application of epigenetics. And our insurance partners are proving that that is a great place for it to be, because the financial and other incentives are there and in place. But where this could go over time is just extraordinary, up to, and as you mentioned, including curing aging. This stuff is fascinating. It's kind of like, once you pull that thread of, you know, how long we might live and things that could impact that, it's astonishing where it goes. And by the way, that's part of why we put together the Human Life Expectancy channel on YouTube, because there's just so many extremely important issues to explore there, that we do that there. But if I go back more narrowly to all right, how do you tell a good test from a bad test? We've said a bunch of things. We've said you want something that focuses on a cause of aging rather than a correlate of aging. We've said you don't want to use something with telomeres or something that has been scientifically proven to be less robust as an indicator. You definitely don't want anything that's connected with snake oil or products or the word toxin, I think, as you mentioned. And you also, I think, don't want just a simple packaged solution. You want something that's customized to the specific group of people that you're working on. And I think also, to that same point, the reason you don't want to just buy a product over the shelf and give it to your customers is you want to have the data. Right? You want to be that company that is helping customers to identify which interventions work best for them. You want to be their partners in enhancing their life. That's not something that, basically, if you let someone else just send you a test and keep all that data, and you're basically giving up what I think is the largest benefit of this, and cutting yourself off from what I think is an enormously robust, stable of opportunities that will inevitably come out of epigenetics.
Mm-hmm. And you had talked about that, and you had talked about our ideal partners in some ways, and I would add to that our ideal partner scientifically is someone who already recognizes the value of that data, is not looking to just throw something over the fence and then get something thrown back over, here's a test and people were in group A or B. It's like, no. Someone where you can share data confidently, confidentially, so that we are improving our algorithms and we are giving them improved results that are very much tailored to their specific populations with their specific lifestyles, ethnicity, etc., so that it really works the best possible ways. And so very excited to find partners who care about that data, want to share that data, and want to improve their customers' lives that
Yeah.
way.
So hopefully you, the listener, are at a point now where you're saying, wow, this stuff sounds pretty interesting. I might be interested in doing this, but how much does this cost? How much do the tests go for right now, and how much will they cost in the future? Well, let's talk about that, Raymond. Do you want to start it off?
Yeah. And it's not too hard to kind of find some answers to that whenever you go out and look at some of these individual commercial tests. People have got these between $300, maybe $500, $600, and that's of course different from what we are talking about and what we look at doing and what that cost is. I will say that there are ways to do this cheaper and cheaper. I think it's less interesting to talk about what is the cost today and what's the cost for all the pieces, and more interesting to talk about what is the cost whenever we are doing this at scale, in bulk, and what do we anticipate this coming to be. We've spec'd out pilots. We've worked with people on some of these different costs. Just the other day, I saw something from David Sinclair, and then saw a similar thing where I think that they were maybe reading from the same book from Steve Horvath, that they both anticipate in the very near future the cost of this being under $100. And I have to say, I think that's conservative. I think that cost actually plunges down much more. And so let me talk about why that happens. For one thing, this is based on most of the ways that we would do this on DNA sequencing technology. And having been one of the guys who helped develop that, I have this great command and understanding of exactly what the economics of that are and what's happened. And as we've seen that plunge exponentially, I can say with confidence that plunge is not done yet. So we will see DNA sequencing get cheaper and cheaper and cheaper. And it's cheaper whenever you do it at scale. So the more the scale increases, the more that actually helps. One of the reasons that's getting cheaper, we always talk about Moore's law for computers, and sometimes we can apply that here because there's a lot of computation. But Wright's law is now the piece that sort of comes into play. And that's sort of it's a fancy way of saying the more you do something, the better, more efficient, and more productive you get at doing it. And there's a nice Wright's law component to doing this that makes this easier and cheaper to do, again, as we continue to do it, not just at scale, but based on the number of times that we've done it in the past. So that's coming into play. And this is being driven not just by gene testing, gene sequencing for research for what we want to do for epigenetics, but both genetic testing and epigenetic testing are a major factor that is used in doing what are called MCEDs, multiple cancer early detection tests. It's probably the most exciting thing to come out in the last 10 years from the Genome Project, where we're able to look at a blood biopsy and get an idea, a very early idea of whether someone has got cancer or not. We anticipate that there's going to be so much of these done that is going to drive the cost down even further and faster than people realize for these base technologies. The other point, and this is a little more complicated, but not in a bad way, whenever we do an epigenetics test, we sort of have an option of doing this very widely or very narrowly. And what I mean is we can look at the epigenetics for an individual and look at every single place where there's methylation in their genome, or we can just sample it and look in a few of the places that we know to be important places. In what we're doing as a company and what people want to do as research and what we want to do, there's a place for both of these things. So especially starting out, we would like to look as much as possible, as widely as possible, because even though we can look at just portions of this and make a 98% accurate prediction, just as accurate as what that wide look would be, we would like to always look widely because there is so much fertile ground to find new things. There's so much fertile ground to find different mechanisms that are affecting different kinds of mortality, disease, tendency for disease, whether or not somebody is doing an intervention that is helping them improve, to go ahead and identify like even types of exercise that work better for types of people. So as much as possible, we want to look very widely and do the more expensive wide test. But whenever we really want to do this at scale and we're not doing that kind of research, we can take this down to, instead of millions or tens of thousands of markers, to dozens of markers and make a change in the cost that is on scale with that. So does this get cheap fast? Yes. Does it even get ridiculously cheaper faster when we're doing this for huge numbers? Yes. Can we go ahead and confidently do this for a lot of people narrowly and think that we're not missing out on big scientific breakthroughs that will help us all? Actually, yes, because what we can do is store samples and analyze them super cheaply, and then whenever we want to, go back and look at them more widely if we want to. So I just wanted to bring up all of those things. Again, the ideal partner for us is someone who understands the economics of that, is willing to look at sharing data so we can do the appropriate kinds of testing and we can look at it and improve it over time. But the cost is not going to be a factor. A nice number to throw around is thinking about this at $100 per test. And that is something that is very achievable in a lot of ways now. And I don't know if you want to talk about kind of this business case, but there's good reasons. And I realize every time I open my mouth and say, this is going to get so much cheaper as we go down, then the next thing people are like, well, that sounds like it's great, so we should wait until it gets cheap to start on this. And I didn't know if that was something you wanted to address.
Sure, you brought it up. Let's go.
Well, I guess my biggest thing there is...
Or I guess another way to say it is, why now? Why is now a good time to go?
Why now? Why not wait another year or another 5 years and see, if it's going to be cheaper later, let's do it later. And that sounds good for so many things. And don't get me started on how we used to say that for real estate, and it was like, oh, I wish we hadn't waited. I think it's a little bit similar. So one of the things is we don't want to start too late because we believe that this is a winner takes most category of business, that the people who are doing this now not only will have the best base of scientific knowledge because of a wide base of testing, but will actually operationally be so much better at doing this that they will have, and we think we do have, an unassailable lead, that no one else can go ahead and look at this and do this. But the more tests that go through this earlier, the wider that lead, the deeper that moat becomes, and the better we're able to protect it. And that's honestly, as a not so much an engineer and a scientist, but as a startup guy, you don't want to be the third person to the party on something where you're needing that lead to be able to thrive. Otherwise, you're going to be watching your competitors do this really well.
Absolutely. Absolutely. So let me kind of jump in here and I'll also maybe backtrack just a little bit. So if I go back to our conversation of cost, I agree with everything you said. I think you got it right. It's that, how much does it cost today? Well, it kind of depends. If you want to do kind of a what I would call a reasonable initial job of doing this, what the test cost today is, let's call it the $200 to $300 area per test. Something like that. That being said, it's very much a function of volume. right? If you're doing thousands, the price is half of doing hundreds, right? And if you're doing tens of thousands, it gets, much less still. As you mentioned also, Wright's Law, you get better at it as you do more. So we think that's going to be a big impact. You also mentioned, and I agree, that it's about the type of test you do. If you go for a broad spectrum test where your objective is to find additional predictors or refine the predictors that you currently have, you need a lot of data to do that, but it's more expensive to collect broadly. Once you've identified a very specific predictor for a very specific thing, the cost of developing a test to do that is actually much, much less than that. So it matters. And then on top of that, there's even new studies out, including one, there's so many studies. We'll talk about this perhaps in a moment. But one study came out, this one just this week, saying that they thought they could reduce the costs of processing these tests by a factor of up to 100.
Mm-hmm.
Which seems quite ridiculous on the face of it. But recall, the cost of sequencing has already come down by a factor of 1 million since the first gene was sequenced, right? If you go from $1 billion+ to $1,000, at the outside, there's 1 million right there, right? So it's already done a lot. And as you say, there's plenty of room to do more. And I think the real question then becomes, who do you want to be in this space, right? I think you want to be the person who's collecting the data, working with this, and riding this wave. An analogy I like to use is surfing. I used to surf in college, so this is still something forefront for me. Once you stand up on a wave, the physics are completely different than when you're lying down and paddling. Mm-hmm. And if you're the one that stood up on this wave early and are surfing this wave, riding on the data and the information that comes in, you're going to be in a position to pick up things quicker and better than anybody else. So there really is an extraordinarily strong first mover advantage in this area. So those are kind of some of the thoughts that occur to me as you mentioned, as you had your thoughts there.
No, that's great. And I'm just in love with that metaphor of surfing, the idea that you don't have to actually make the splashes and make the waves. The waves are already there. The data is coming. The technique has happened. You don't have to be the person developing the technique. It's, are you going to use what's going to basically be this free data laying around? And are you going to have business processes that take advantage of this? And the way you get to be that person, that organization, is you start now and figure out how you can make use of it. The other piece with the surfing, as you're going down the wave, this is also the place where you get to pick and choose where you're going. What are your particular points of insight going to be? What assays do you want to have? You can start broadly and then develop particular ones. Again, you don't want to be a slow follower. You want to be a fast developer, and this is what we're seeing works really well. It's amazing the new number of applications that are coming out. And I know we wanted to talk about some of these new pieces. I was just going to mention, this is not just like, what is somebody's cardiac health like, or can we tell something about risk from respiratory from smoking history, and yes, and that's almost like old news. We're able to even start to see, can we go ahead and tell whenever somebody is informed of their risk of this, how likely are they to adopt these particular interventions? Like basically, whenever you're trying to help them and let them know, here's stuff you can do, who are the people who this is going to be really effective with, and who are the people where it's not? There are things you wouldn't imagine that you would be able to apply this to. This becomes super predictive and super helpful, so that you're really devoting your resources to doing the most good for the most people.
Absolutely. And again, it's in its nascency, and those who are here at the beginning are going to be in a position to guide the development in a way that's most advantageous for their company and their people and their country, right? And those that are left behind are going to be the ones that will suffer the adverse selection, or will basically only pick up the technology after many of the benefits from an economic standpoint might well have been spent.
Shit.
So there's that. What about on the scientific side? I had mentioned that, we, of course, we're in the nascency of this, but there's a lot going on. I'd mentioned on the processing side that costs could go down, including one article that said, the costs of the processing could go down by up to 100 times. But there's plenty of other advances in the science that happen almost weekly. There was one this week that came out talking about how you can infer biological meaningful insights from epigenetics. There was also one that plenty of studies continually show that interventions can actually produce lasting changes in biological age. There's always new studies coming out about that. And again, it's just such an exciting realm. I wondered if you had any broader comments on the science and where it's going and what we should look for going forward.
Yeah, I guess I look at it, there's like 3 or 4 like broad categories where all of these new studies fit into, and just to kind of tick them off, because otherwise you ask me an open-ended question like that and I will go deep in the weeds and 3 hours.
Well, maybe we should do that in a separate video sometime. We'll do one just on the science and recent studies. That might be fun.
I would really love that, and if people respond, I think that'd be great. To maybe we could pick a study or get somebody to pick a study and tear it apart a little bit and talk about what the implications are. But I would say the broad categories. New technologies and new techniques in the technologies that we've got that are reducing the costs of this and giving us greater insight, because it's not like reduce the cost and the quality, it's reduce the cost and still give great data. So that's a whole thing right there. And there are particular conferences that we watch. One of the great things I love about working with you on this is we've got this fantastic group of people who we all, it's kind of like we're the epigenetic current underground, and we communicate back and forth. We've got a server where we load papers up and we talk about them and what does this mean for that. And so I think that I'm always on top of things, and if I have found, I don't even find half of the things first. I find maybe a quarter of them, and I'm always surprised by what other people find. So that's great. Another piece that I think we have really been on top of before anyone else is this idea of the systems biology behind all these things. And so instead of just saying we can take a whole bunch of numbers from a whole bunch of different methylation points in the genome and sort of combine that into this grand equation that predicts mortality or predicts biological age, we're now able to break that down and say, okay, here's the part of the equation that's for cancer risk. Here's the part of the equation that's for cardiovascular. Here's the part of the equation that is actually predicting something about respiratory. Here's the part of the equation that's this. That is spectacular. And while I think we were in a lot of ways first to the party on that, we're seeing more people show up at the party, which just makes it a more interesting party, and new results on that every day. And in the last 2 years, because we've been looking at this for several years, we've seen some of these main research groups really come down hard on this and say the real value in this is being able to do specific predictions on specific therapeutic areas. In addition to that, sort of the part B there is being able to do specific gauges of not just what might be wrong with you, but what you're doing to improve it. So it's been kind of hard on an individual basis to say a specific kind of intervention is really having an effect. We are starting to see that now, and really good data coming through where you can look at a person and say, after this much exercise, this person, not just as part of a group where it's statistically significant, but this one person is doing that. That in just the last few months, that's something that we've had as a hypothesis we've been working toward. It's now starting to show and be replicated, and we're seeing more and more of it. That's just amazing. The piece that I think, and like I say, it's a little Buck Rogers, but the idea that this is not just a great indicator, a great number, but it's intimately associated with what is happening with aging, and the epigenetics is a formative mechanism and that because of that, you can go in, get your epigenetic wrench and change the setting of some of these things and actually reverse pieces. And we're seeing that in probably two ways. We're seeing people who are doing interventions that are not crazy. They're different, pieces with lifestyle, exercise, and diet. And then it's showing up in their epigenetics and in other forms of general health, other kinds of endpoints, like you were saying, that you can measure, where they look healthier and younger, and subjectively and objectively, it's doing some good. But we're just starting to see some of the first studies where you can go in and do maybe some more major interventions on, using drugs, using growth hormone, using metformin, different things, and it shows up. We're also starting to see where you can go in and just directly reprogram the epigenetics. And some of these are cells in a dish versus rats versus, your next door neighbor. And that's always the scale that you should look for. But I think they're really significant. It's amazing what may be down the road. So the value of understanding these epigenetic patterns, how they work in different populations and in individuals, being able to apply that to, so brilliantly whenever you had first talked to me about this, the business case of using it in insurance, where you have the widest scale possible tracking of outcomes and where people really care about getting it right. I think that this just has such an amazing future. And so we want to continue to track these things and talk about them more publicly and bring this to more people.
Absolutely. So let's do that. I think our current database has, well into the hundreds of different studies that we've all considered seminal at one point or another on epigenetics. And of course, there's much more to come. Well, Raymond, we've been going at this for some time now. I want to ask you, are there other things on your mind that you've wanted to say that I haven't found a way to ask you?
No, I feel like we've covered some really great pieces. And as always, we have such a great back and forth. Thanks for letting me jump in and interrupt. And I look forward to doing this some more, either deeper on particular pieces or on the technology, on articles, or I really want to show people some of the things we've done on some of our pilots.
Absolutely. Well, I think you know how much I appreciate your guidance and insight and friendship in all of this. I couldn't ask for anything more. Raymond, thank you so much.
You
too.
So
listen, thank you so much. So for those of you who have, now that you've stuck with us through this whole long thing, first of all, congratulations, thank you. This is not the last piece, though. There's much more to do. We've got more videos to come out. The science is evolving quickly. We will talk about specific studies. We will keep you updated as epigenetics and insurance progresses. And do want to encourage you, if you haven't yet, give a look at the video we've already put out there on genetic and epigenetic testing, which talks about the process and the history and the discovery, much more. And also feel free to check us out on our website at Human Life Expectancy Inc. Thanks so much for joining us. And as always, please, let's do what we can to help ourselves and help us all to live longer.